always have a borrow of 0 because there are no less significant digits for this column. 1 minus 0 is 1, does not have a borrow. 1 minus 0 is a 1 with no borrow. Since we did not have a borrow in both cases, we put a 0 as the borrow from this. We put a 0 here because we are not borrowing anything from the next digit. 0 minus 0 is 0. 0 minus 0 is 0 with no borrow. 1 minus 1 is 0 with no borrow. 0 minus 0 is 0 with no borrow. 0 minus 1 is 1 with a borrow. 1 minus 0 is 1. All right, and this is it. I'm going to stop here. It is not, quote unquote, a negative number. How can that be? Because in decimal, we always end up with a negative number if we're subtracting a larger quantity from a smaller quantity. But my question to you is, how do we represent negative numbers when all you have are zeros and ones in the memory of a computer?
Distance from 0. Distance from 0.
Distance from 0. Yep. Well, yeah, we're going to get to that part, okay? The most significant bit becoming a signed bit, yes. Okay, that is actually what we're going to do. But on top of that, we are also going to use what we call 2's complement, okay, which is a kind of really magical kind of thing because with 2's complement, it will do the same thing as what you just described. The most significant bit is the signed bit. It will tell you whether the number should be interpreted as a positive number or non-negative or negative number. But it also makes it possible to do subtraction and addition very easily. Okay? It makes no difference whatsoever whether the number is supposed to be signed or unsigned. So we'll get to that point a little bit later. But for now, all we are stuck with is just bit manipulation. Okay? So this would be the final answer. If I have to subtract a 4-bit number from a 4-bit number, this will be the final answer. Okay? We end up with a 4-bit difference and an extra borrow. In this case, an extra borrow of 1. It doesn't seem to be useful because it's just one extra bit sticking out into nowhere. But as I said a little bit earlier, that bit turns out to be extremely useful later on when we talk about comparison. Are there any questions about this? Yep, go ahead.
Does that bit have to do with parity?
No, it is not parity. It is called the carry bit, which is also known as the borrow bit because it depends on the operation. It allows you to do several things. One is for unsigned comparison. And the second thing is you can actually use that to extend subtraction or addition to deal with a width that is wider than the ALU, than the processor can natively handle. So let's say you have a 64-bit processor, okay, which means it can add and subtract 64-bit numbers at a single with one instruction. You can deal with all 64-bit. What if you have a 128-bit number? Then you need to separate it into multiple operations. This extra bit here allows you to kind of daisy chain your instructions so you can deal with numbers of any width easily. So we'll get to those instructions, subtract with borrow and add with carry, but that's kind of like a few weeks down the line from here. All right. So are there any other questions? No other questions? All right. With no questions, we move on to the next section, which is really just a summary because we are pretty much done with binary subtraction and addition. This module makes it rather clear that not only can we represent numbers in binary and perform addition and subtraction, but it's actually easier because you don't have to memorize and say, oh, what is 2 minus 7? Because 2 minus 7 is 5 with a borrow. But the only way you learn that is first, you count your fingers, and then 2, you memorize everything, right? But in binary, there are only 4 cases. It's very easy to handle. Don't you think we should change our number system from base 10 to base 2? No.
It takes up far much more paper space.
Then okay, well, that's another solution to that. We go from binary to base 16 to hexadecimal numbers. We do all the calculations in binary, and then when we write it down, we convert everything to base 16 to save space.
We have the decimal down.
Sorry?
We have the decimal down, so we're good.
It's just a habit, okay? You know, base 10 is nothing more than a habit, okay? And not a reasonable habit either. It's not logical at all.
We'll start teaching our kids hexadecimal. How's that? We'll do everything in hex.
Hexadecimal in multiplication is really hard because you know the multiplication table is huge. So you only want to do hexadecimal when it comes to writing down the numbers, representing it. Okay, but when you do the calculation or understanding how to calculate, you know, base 2 is easy. Okay, even for multiplication and particularly for division. Okay. You guys understand why division is harder than multiplication, right? No. Do you? Because in order to do division, you really have to get multiplication down first. Okay? If you don't believe me, I'm just going to write this on the board, but I'll kind of say it out. You know, okay, so we have a huge number here. All right, and we use a big divisor too, so it's not obvious. All right, so in your mind, you actually have to do multiplication or have a rough idea of how many of these we have in this, right? That's division. Now, in this case, it looks too simple, right? So if I make this a little bit harder, okay, just flip the 2 and the 5. So now it becomes 5204254420781 divided by 12741. And to do this, to perform this division, you have to do multiplication in your head to figure out what number you should put here as the quotient, right? And once you kind of have a rough idea of, okay, I think it should be this number, multiplying this number to the divisor also requires you to do all that stuff in your mind because you don't have a lot of space to actually do it. In binary division, it's very simple because you either have one of those things or not. Right? There's nothing you have to do. There's no multiplication involved. It's only comparison. Is this number bigger or is this number bigger? If this is bigger, if what you're looking at in the dividend is larger than or equal to the divisor, you got 1 over here. If it is less, you get 0 of those. I think that's easy. Okay, and that's why I think using decimal numbers, we are actually wasting a few years in elementary school education just because we picked the wrong base. And the funny part is universal. The entire world is wrong. There's no one single culture that I know would use binary numbers. All right. So enough of that stuff. Moving on.
60 symbols.
So moving on to bad return. We talked about that already. So now we'll talk about adding and full adding. Okay. So we are looking at this one in a different way. And all right. So what we are really doing here is to figure out how do we do all the addition and the subtraction thing. Okay, how did we do it a little bit earlier? Let me just go back to the example, and I will ask you, how did you figure that out? Okay, so let's start with the new example. It's always easier that way. Okay, 1010 minus 0111. Okay, that's a new example here. This entire row are borrows, so we stick a 0 here. All right. Tell me why you know there's a 1 here.
The 0 minus 1
Because I said so, right? 0 minus 1 is a 1 with a borrow. So that's why you know there's a 1 here and there's a 1 here. Now we have 1 minus 0. How do you know there's a 1 here? Because I said so, right? Okay. Well, also because in arithmetics it makes sense. Okay. All right. So now you have the entire table of 0 plus, that's subtraction, but I can deal with addition here. 1 plus 0 0 plus 1, and then we have 1 plus 1. Okay. So on the other side, we have the actual result of the addition. That equals to 0, that equals to 1, that equals to 1 again, and that equals to 0. And over here we have, okay, let me just make this very clear. This is our carry. This has a carry of 0. This has a carry of 0, 0, 0, and here we have a carry of 1. Okay, in terms of arithmetics, in terms of adding two things, and getting the answer, that makes sense. Are we okay with that? Yeah, that makes sense? Okay, so instead of looking at this as addition, what if I say this is a mystery operator? Okay, this is just some kind of mystery operator, and it has two outcomes. One outcome would look like this, and the other outcome would look like this. Okay, and I'm going to tell you and say that, guess what? The computer doesn't know anything about addition. It only knows something about or, and not. Or is disjunction, and is conjunction, and not is negation in logic terms. Okay. How many people need a quick brush up on all those logical operators? Okay, quick brush up. Coming up. Okay, so we have the AND operator. Okay. So let's see. We have x, y, x and y. Okay.
And or. Could it
Yeah.
be and or?
No, AND is by itself an operator, or is by itself an operator.
It could be and or for those conditions for the question mark.
No, it's just a mystery operator. Okay, it's just the one way to relate two values and give me, two results. Okay, 2 bits as results. Okay, so in binary, what can x be? 0 or 1. Very good. So x can be 0, x can be 1. When x is 0, y can be 0 or 1. When x is 1, y can be 0 or 1. Have we seen anything like this before? Except, 0 is interpreted as false and 1 is interpreted as true. For those of you who took cisp310 from me, that should look familiar, okay? Because that's exactly how we introduce the conjunction operator. All right. What is x and y? 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. Oops. And 1 is 1 is 1. Because 0 represents false and 1 represents true. Is that okay? So that's a truth table. This table defines what is conjunction, what is and. Can I possibly be missing something here? No, because I have enumerated all the possible cases for x and y. Because x can only have values of 0s and 1s, and y is the same way. So when x is 0, y can be 0 or 1. When x is 1, y can only be 0 or 1. I have enumerated all the possible cases. Let's look at OR. Okay, so we have x, y being independent variables, and then we have x or y here. When x is 0, y is 0. What is x or y? 0. When x is 0, y is 1. What do we have as the OR? 1. We have 1, 0 here. 1, 1, 1. Oops. 1. Exactly. So that's how